helpful during the project because it gives a really easy framework to work with compared to just doing it on Torch. So let's get started. TorchRL is a reinforcement learning library for PyTorch. While this was being built, the things that were being focused was high modularity, few dependencies, and generally aimed at supporting the research in RL. The way that it was built was to try a bunch of different policies, bunch of different environments to be able to train models fast with least code as possible. It was developed by Meta, just like the standard PyTorch. And using it is pretty simple. It doesn't require a lot of libraries. It's just people TorchRL, and it works. Currently, they have version 0.10. Although the new version sometimes makes some dependencies, I would suggest maybe working on the 0.7, 0.8. I think it would be a good version. I use it myself and I haven't encountered any major problems. So let's start with the environments. It is the key for reinforcement learning. An agent needs to be functioning in an environment, and our agent loops through this environment. We call this model our policy with the action and the state that is coming from the environment. And our goal in reinforcement learning is to have reward signals that is given to our agent to reinforce the good behavior. This is the basics of reinforcement learning. How we usually do in this course and many of the reinforcement learning applications is we have a simulator that accepts actions as inputs and produces an observation along with the metadata of output. This could be the reward signal, this could be done information. It used to be done, then they changed it to truncated and terminated. So the difference is actually really simple. The done was just when the environment finishes. So it should require a resetting. Terminated means the behavior is completed. Truncated means, let's say I have an agent, I say do 700 time steps, and when it's done, it will truncate automatically, whether it's completed or not. So that's like the differences. So there are a lot of frameworks to train a reinforcement learning agent. Gymnasium, you probably heard of already. There's DeepMind Lab. There are more libraries about using environment simulators. We're going to focus on Gym again, since you're already familiar with it. You might have already known that Gym already provides us a lot of basic environments. I have shown some of these here, like hardball, that was the homework one, as well as some mountain car, acrobat, pendulum. All of those are like pretty simple toy examples. But Gym also has harder environments as well. But we're going to focus on this. In order to use Gymnasium, we are going to use their built-in wrapper. How it works is pretty simple. We just import the gym end, and we are just going to call how we call the Gymnasium, and it is going to be wrapped for TorchRL so that we don't have to do any changes. So now I'm going to focus on what makes TorchRL simple and very modular. So they call it TEDS, TorchRL episode data format. Now the environments function on two main functions: the reset and the step. The reset is the environment, and the step function takes the input of an action, sends it to the environment. The environment steps this through this action, gives me new state, reward signal, and done information, and many other metadata outputs. Now, on Gym, as I said, we have observation, reward, and done. Right? But in TorchRL, instead of getting those information separately, we get it in a structure called TensorDict. So TensorDict is explained as generic key-based data carrier for tensors. It doesn't make sense on this explanation, but super simply, tensor date is a dictionary of tensors. That's how I explain it to myself. So instead of getting those different variables, we just get a dictionary of tensors, and we operate everything through this dictionary instead of handling like on different things, trying to catch dependencies, making sure that all of our variables working. We just have one main dictionary. So this is the novel part about TorchRL that makes it super simple, because everything will be written to one single tensor date. Observations, rewards, actions, let's say if you're doing continuous, our probably distribution function, etc., everything through the tensors. So a tensor date looks like this. It looks a little confusing, but if you look at all the fields, you can see action, done, next, observation, terminated, truncated, and in the next you can see another field which shows you the reward and the next observation, the batch size. So this is just an example. So I can show you in Colab how it really works. So we can also do some coding. So in order to start with the TorchRL and TensorDeep, you just need to have those two libraries set up. This should be probably enough, but based on if you would require some additional things, you could also have like different libraries such as if you're logging TensorBoard, CSV logger, etc. But this should be enough to start with the TorchRL. So we also have to have TensorDeep separately. So while this is loading, I can explain. So here we just use the standard wrapper in the gymnasium. So I'm just importing here the pendulum v1. So this should be yeah, should be done soon. And yeah, and I'm going to just show you what happens when we reset the environment. So we can see the fields of done, observation, terminated, truncated. This is just the resetted environment. So we're not going to see any action, no reward, nothing. Just the first initial step. So they have some functions here. A random action reset. So it resets and takes one single action. So here, when we do that, we can also see this action field here. Here you can see that this is on float. This is size of 1 because this was there was no batches here. It's just one action. And if you look at the action, it's just going to be tensor. So you might have already know that the PyTorch functions on tensors. And converting normal variables into tensors is really duty heavy for computers. While when we have everything on tensor, we never have to do this loading unloading phase. So this actually helps with the efficiency as well. So if I step the environment, then I'm going to see the action that is affecting the next field. So the next field is basically everything gathered after the action was inputted to the simulator. So this observation, this terminated, truncated information is the one that is S, the state, and this is the S prime after the action. So this might be, let's say, not done, but after I take this action, this might be done. So this kind of gives us a structure about seeing what action affected the state how. And again, if we do the step EMPP, we are just going to see our standard output again. The next is going to be our current state. Luckily, we don't need to do the loop. We can just do a rollout. I just specify I'm just going to roll out for 10 actions. And when we get the rollout, you're just going to be able to see that there's 10 different actions, 10 different dones, 10 different nexts. so we can see the entirety of a rollout in one tensor thing. So this also helps kind of analyzing how it works. And what's really good about it is you can just pull out a specific rollout, and let's say like the third time step, we can also see what action was being taken. So everything is written super clearly, and you can just function through that. So this is why TEDS or TorchRL episode data format is really useful. So we talked about environment, but we usually don't use the environment as it is. We need to do some transformation. If we want to add some things, the environment needs to function in a way that we want. And transforming an environment is usually hard. Luckily, they have added the modular way of transforming these environments the way that we want. Let me give you an example here. Step counter is a really simple modification on the standard environment. When you start with the reset, we start counting our steps. So it starts 0, 1, 2, and that's it. That's a super simple thing. But if you would want to do this to our current gym environment, we would need to write some code. And it's add up. When you add more and more and more codes, it's just going to be a little bit harder to handle, and small bug might affect it. And if you do the step counter here, we would just need to import this step counter, and we use a function called transformed environment. So the transfer environment, you can just add the current environment and the transformation that you would want to show, and when you do it, it's just going to be transforming with the way that you want if the TorchRL have the option. So let me show you some examples. I started with step counter. When we do the step counter, I'm just going to add it through this function. I just add a step counter. I said just for the 10 steps, and I have a rollout of 100. So when I do this, I can see my step count here, add it to this tensor thing. And when I want to pull it, I can just pull it, right? But this seems not really important. It's just a toy example. I can show you things that actually matters. So reward scaling. The rewards that we gather from the environments are usually on scale. So it could be like 100 or 1,000 rewards. But this reward being unscaled means that our value function needs to predict really high numbers. And this is usually something that we don't want. So let me show you an example. Here, if I look at this rollout, if I look at the rewards that are being given to me, it started like negative 0.7 and goes all the way negative 9. This is for a model, it's hard to predict because the scalar value increases, so our value function needs to keep track of it. If I want to have my model predict least big numbers, what I can do is I can call the reward scaling. I can scale the rewards between 0 and 1, and I can just edit with the transform environment method, and if I roll out, it's just going to roll the rewards in between 0 and 1. So this one is negative 3 because it scales the rewards within the environment. So let's say if I roll this one, the first 10, then it's going to be, of course, not scaled well. But if you, let's say, if you can adjust 0.5, then yeah, then you can, scale your rewards however you like. Another example that I can give is the init tracker. Now this one was particularly useful on my research. It is really, really simple. What it does is, when I call this init tracker, it just tells me when it started the environment. So usually we know when the environment starts, but let's say we use a recurrent model like LSTM. And LSTM needs to be resetted, their hidden parameters on every reset, so that we don't carry any information from a previous run. And if I have this init function, I can just reset the LSTM parameters whenever I want without an extra burden. So these small transformations actually really help a lot. So moving on to modules. As I said, TorchRL is really modular. Everything can be added like Legos or puzzles. Just like transforming TensorDict, you can transform policies as well. And the way that we transform the policies is really simple. All we need to do is, if I have a network, I'm going to specify what's the input through this TensorDict and what's the output. And this is automatically going to be connected, and any network can be a model or a policy. So TorchRL provides us with some wrappers, like actor, probabilistic actor, all these things that automatically wraps my network into a policy. I also have networks that I can use, a standard MLP, a convolution network, or an LSTM module. These are also all wrapped for the TorchRL so that it can function with TensorDict. Let's say if I want to do a DQN and I want to do some exploration, I can have a e-greedy module added into this, and many other things. So let me show you in the code again. So here, I'm going to have a lazy linear. This lazy linear is a standard, really basic network, and I'm going to just have these output features match with the action spec. And when I want to use this module, I put this module inside the TensorDict module, and it is automatically gives me with the input and output a policy. Because since it's already reading the environment's TensorDict, all I need to show is this is your input and this is your output. And when I put this policy into this rollout, this policy is the one who's taking the action. So, but if I don't want, if I'm extra lazy and I don't even want to put the input and output, they even have a wrapper. So let's say if I want to have a discrete action space actor, I just added my module into the actor, and it becomes a policy. And since I already know that my observation should be observation, the action is action, so all these have some structure, I don't even need to add anything. I can have a network, I can put it onto a wrapper that I want, and it just works. And for networks, you also have a really good amount of variety of choices. So instead of a lazy linear, I can put it on MLP, I can put some cells, and I can even add some activation. And using this module, I just put it into this actor wrapper, and it becomes my policy, and it works again. So you can, let's say if I want to experiment it with the things, I can be, maybe this is too small, I can just do 28 and run it again. Or I can just, instead of 10H, I can do a different activation. So all of those are like, kind of gives us an easier time doing research. We can just plug and play different things, and what makes it really nice to play with TorchRL compared to just standard Torch. Again, for policies, let's say a TPO, our policy needs to be stochastic. So instead of getting the action directly, we're just going to get the distributions. In order to use this, I'm just going to convert my output into a mean and standard deviation of size 1, and I'm going to use this as my distribution. And what probabilistic actor does is it takes this distribution, converts it into an action. So I don't have to worry about that too. So again, I have an MLP, and I identify my extractor so that I get a probability distribution function. And what I do is I just connect two of them with the standard torch sequential, and this becomes my module. So the output of the backbone is going to be the input of my extractor, and two of them together becomes the module. And what I do is I put this module, TensorDict module, again, it needs to be wrapped. The standard, like any network won't work without wrapping. I'll just use this TensorDict module instead of a standard wrapper. So our input and output keys needs to be specified here, and this becomes my TensorDict module. What I want to do is I want to wrap this into the probabilistic actor. I put my module, and I put this time my input keys as the mean and the standard deviation. And this then turns it into my action. Because probabilistic actor here wraps the mean and standard deviation into the probability density function, and then I use this to do the exploration. And when I run this, I'm going to be able to see the action log probabilities, the actions, the scale, which is the standard deviation of location, the mean. So you can also have access to all of these. So nothing gets lost, and everything is there for you to, just check it out, just to make sure if it works, just to see what the outputs are. And let's say if I want to do some sort of different exploration, I can do a deterministic exploration type, and I can do a random type. And I use this via the set exploration type method. So this is just one type of exploration. Usually we don't want to just do a deterministic one or a random one. What we want to do is in DQN, let's say, we want an E-grading policy so that we can decay the exploration. So my agent in DQN starts with really random actions and slowly convert those actions into more deterministic ones, so that while I explore, I also try to learn which actions make sense or which actions give me more reward. So here's E-grading module, very fun and easy to use. So I have an MLP network that is wrapped under the actor, and that's my policy. And I have a separate exploration module. I just put the action spec. The reason that we put action spec is when my E-grading module wants to take a random action, it needs to know which actions are possible to take. I have an annealing numbers, epsilon initialization, all these parameters, and I automatically get this module. And if I just put those back to back, it is just going to look like this. So I have my module here, and I have my E-grading module that is like kind of put together like puzzle pieces, and this is like end-to-end from observation to action works. And if I want to see again, I can just change my exploration type to deterministic. This turns off the exploration, or turns on the exploration. So we can also have these kind of different ways of changing the exploration on command. So I would like to put everything that I discussed so far into one Q-value actor. So far we talked about the modules, the wrappers, the actors, the environment transformation. So let's use our good old example, carpol. Carpol is really simple. I put one that if you haven't seen so far, it basically kind of kills the cart so that it just tries to have this pole standing. So there's just two actions, and the observation space is really small. So it's just a really nice toy example to start with. So I have my observation that I'm going to put my MLP, and my MLP is going to output two action values, right? And then I will put a Q-value module, which is just the argmax module. This is going to get the argmax of the two actions that I give, and I will put another E-grading module so that I can do a decaying exploration, so that my agent is going to do some random things and slowly converge into more deterministic. This way I'm going to be able to see a lot of states and not fall under just one way of the game. So the standard MLP is just going to be my value net. With the Q-value module, it's going to be a deterministic policy because I do argmax and I get an action. And when I add an E-grading module, it's going to be an E-grading policy. So what we're going to do is, again, I have my carpol, I have, even you can see like the action spec here. I have my actions S2, and I'm just going to put this MLP with the input and output so that it's a tensor module. This is value net. This is what it looks like. Lazy linear followed by an activation, another followed by an activation. And I will put my Q-value module so that I can argmax. So I don't have to write any code for that. I have just added here. So now this is going to be the argmax. And when I roll out a policy, you can see my action value, all these things. So what are those is? The action value is the one that is outputted by MLP. It outputs two actions because I have two actions. These are just numbers of the probability that which one should I choose, because what I'm doing is a function estimation. So that means basically if I take this action 0, this is going to be probably there. And how we choose it is, standard DQN is argmax. I just get the highest one. That's what makes it deterministic. So between two of these, this is the higher one. So I will pick one, etc. And what action look like is just the one had encoded. So it just says to me that I should just go for the left. And if I add this eBridge module here, and if I put it onto random, again, I can see the chosen action value and the action value. So what are those is, let's say my action value is here, and my actions are here. What you can see is, this is the argmax, and this is correct, right? But if you take a look at this one, we should have picked this one, but instead we picked the other one. The reason is that when we were doing the exploration, we did the random. So the eGrid function here, and the epsilon is 1, is basically taking random actions. So it doesn't depend on what my outcome, I can do different actions. So that's just a way of seeing that our eGrid module is working. So now we covered the DQN, how to make a classical DQN. As you can see, it's just a few lines of code. Once you have everything ready, it's just connected like Lego pieces. So, but we missed a really important step. We know how to create an environment, how to play with environment, how to create agent, but without training, an agent will just not work. We need to train our agent. We need to update the parameters. We need to basically optimize our model. So just to do a small recap, what value function predicts is the return of the target, the reward plus the discount of future rewards. And in like value-based methods such as the DQN that I show, we approximate the Q function. So what I'm optimizing is the MSE loss between the predicted Q value and the target value. And the loss looks like this. In policy gradient methods, we maximize the expected reward. So we get a negative expected return, and the loss function is like this. It's just too much math for me, and I don't like too much math. So what I will do is I will just use TorchRL. What we are going to do is, in Torch, you might remember that we use loss backwards and optimizer.step, right? But in TorchRL, we have dedicated loss modules as well. So everything is modules. The actors connected like modules, model optimizations are modules. We just add them together. Let me give you an example of like the off-policy DDPG algorithm. So we need a policy defined as the tensortic module. We already covered this. Our policy will be a value network for predicting the value of state action pair. The DDPG loss will find the policy parameters that output actions that maximize the value for a given state. So we are just going to try to find the return or the reward plus the discounted future rewards. And we will need an actor and a value net for that. And then we will train our loss module function. And I will also show this soft option. So going back to the code, we have covered some of these already. We have the observation space, the action space, and I put those into the actor wrapper, so I have my actor. And for the value net, I again put a network and the input and output keys to have a value operator. This is also another wrapper. And then what's novel in this one is the DDPG loss. TorchRL for most of the different modules gives us the loss module ready. So it's just a plug and play kind of way. So when I put this DDPG loss and start rolling out, I can see loss values. So there are different losses. We have loss actor, loss value, other things, and in order to train our models, we need to get the loss functions. Here, my loss actors is 0.1 and my loss value is 47. And I can just combine those two into one loss number. And you know, just like how we do in normal torch, we just need an optimizer. Let's say we use an optimizer. We will put the parameters into my optimizer to the loss backward. This is the backward propagation, and I'm going to step my optimizer. And for the next one, I need to zero the gradients again. So this part is pretty much every single machine learning how it works. The only novelty here is that I didn't work for the loss function at all. I just put my enter and value, and I automatically get my loss. And for bonus, I want to show what is soft update. So it's already been covered that on the Guven or any other model, we have an overestimation bias. So once we are trying to follow the target value, we just overestimate the values more and more. So it just becomes more and unrealistic. In order to solve this, we simply do a soft update. Instead of updating the target super quickly, we just update the target a little bit. So the target follows from the behind, so that we don't do the overestimation bias. For that, they also provided a soft update method. So to the loss, if we add the epsilon, so to the decay, we can have an updater, and we can use this updater as well. And I'm going to show how it all connects on the next coding tutorials as well. So data is learning. In order to do machine learning, you need the data. And you might be thinking that yes, we need data and labels to learn a basic module or basic policy. But even if you don't have labels, we can use it via the rewards. But it needs to be structured together so that we can put it onto the batch, so that we can feed it onto the network, so that we can learn. So we basically need to collect the data through this environment. What we use is the data collector. So the role is really simple. We are going to execute the policy within the environment, reset when it's necessary, and provide the batches. And it just requires what my batch needs to look like, what should be the length of the iterator, what's my policy, what's my environment. And once it's ready, it just looks like this in a pseudocode. Just you put the collector into this for loop, you get the data, and let's say if I want to get 2048 frames, I just put it in, and I'm just going to feed it into, and then I will update my parameter and optimize my model based on the data that I get. Another way, not every model uses, but some models like DQN, the replay buffers. The replay buffer just stores data temporarily. When we collect data, we put it into the buffer, and then we get it back, we sample it, and then we update our model. The good thing about it is, since we have a variety of data that is collected within different episodes, we can have a smoother model, since we can remember both the old collected data and the new collected data together. So for that, we're just going to have storage type, sampling technique, writing heuristic transform. We don't need to have all of those. We can just make TorchRL do the calculations for us, and we can just initialize a buffer, store when it's in the out of collector, and sample inside the optimizer steps. So let's see how it works. When I start, I'm going to just have a gym environment, just a random policy, and the sync data collector. What makes it synchronous is it starts with the environment, and it goes like from the start to the end. The async one, if you have multiple environments, they play the game at the same time. So I'm not going to cover async because it's a little bit more about the multiple environment and efficiency. I'm just going to cover the sync data collection. I put my environment, I put my policy, I put how much frames that I want to get, and the total frames. If you put -1, it's just going to go for eternity. And if I just put the collector into the for loop, I'm just going to see a new field here, the collector. So in collector, I can see the trajectory IDs, the batch size, etc. So we just get a new field here. What this field looks like is, if I look at the trajectory IDs, I can see it start with 9. I run this before, so it normally starts with 0. What it does is, in the 10th environment, I run all of those, and then my game ended, terminated. So in carpool, when you do a bad action, the poll just falls down really quickly within a few timestamps. So in here, it stops. It knows that it's terminated. It resets the environment. It starts again. So everything is handled through this collector. I just give the environment. I just give the collector. Since I'm already wrapped the gym environment into the TorchRL, it just knows when to stop, when to continue. So I don't need to worry about resetting the environment. I don't need to put a if done, then like break into the new one and then reset each time. All of those things can be handled. So it just gives a compact coding method. For the replay buffer, I have the directory of where I want to put these, and I will start my replay buffer through this buffer. So it needs a location to use. And what my replay buffer looks like is I have the data, the shape, the length, and the max size. So everything is again a tensor bit. And if I just extend the data, which is just means that store it into the buffer, we will see different indices. And if I want a sample through 30 different ranges, I will just see my collector has 30 different samples, and I have 30 downs, 30 action, etc. for all of those. So loading and unloading is literally extend and sample. That's it. Just it's really easy to use it, because usually if you want to implement yourself, it will be a little bit harder. But everything is optimized. It just loads and unloads with just one function. Finally, logging. We need to check our algorithms. We need to at least see if it works or not. If you have, let's say, thousands of episodes, you're not going to be able to look at just the loss. You would need to have like some graphs, some tables, some analysis, so that you can kind of track what's going right or what's going wrong with your agent optimization. For that, there are different methods. CSV logger is a good example. TensorBoard, I use it personally. I really like it. Weights and biases, WANT-B, it's also really good. A lot of reinforcement learning people use it, and many others. And other thing about logging is graphs are cool. Graphs tells us a lot, but not the entire story. When you see an agent that performs okay, and you see, okay, my agent's probably really good. You put a video, you watch your agent, and it's just bad. It just, if you would play it, you wouldn't play like this. So it is really important to watch your agent, and it's one of the ways of logging it, so that you can see if there's something inefficient, something, the reward hacking. If my agent is stuck on a small loop of shaping reward hacking, then it's just going to have a lot of rewards and a low loss, and you're going to think that, oh, it's just doing amazing. But once you see it, it's just going to look really bad. So let's see how we log and how we watch our agents. So I'll show it with CSV logger, but pretty much every logging method is pretty easy. So now we're kind of out of the TorchRL region and more into the logging region. So when I start my CSV logger, I will just put an experiment name. And when I run this log scaler, this is just to store one thing as a example. I can look at here and then see that it's just right here. on the CSV method. So every data can be written like with just one line. So the second thing, the cool thing, is recording videos. So in order to record videos, we need to have the pixels so that we can transform those pixels into videos. What we're going to do is we're going to say from pixels true and pixels only false. So this one gives us the pixels into the tensor data. And this one makes sure that we're not using pixels in our module, because the carpal example have only 3 observations, so it just gives us the line, and because of that it's easy to learn. But if you were given an image of 400 pixels to 600 pixels, then we would need a convolution methods, we will need to image decoding, all these things. We shouldn't really work with the images. Of course, in some reinforcement learning methods, we work with images, but for this example, it's unnecessary. So that's why I said pixel only false. And when I run this, I'm just going to see again the classic things plus the pixels. So here I have run for 3 time steps, 400 to 600 image. So this one's batch and this one is the time step. And if I want to see my video, what I'm going to do is I'll put a big video recorder. This is also added into the environment because it needs to be able to read those pixels so that the TorchRL just handles it for us. And I will just run this 30 times the rollout and dump it into the recorder. This is a required function for the recorder to work. And what I will do is I'll show you what it looks like. So I dumped it. It's written in this my video 0.pt, and this looks like this. This 3 is the 3 time steps, and this is the pixels. And so this one is like particularly for the collab to be able to see. But what we essentially do is we have this frame pixels. We turn this frame pixels with a choice of our library. Here I use image.io, and we can turn this into the image of a GIF. And from start the GIF, I'm just gonna be able to see. So now we can just play our video. We can see what's going on. So we can see that our image is pretty, not really optimized because we didn't train anything. Right? So it's just going to fall easy. Okay. So we have covered everything, and the only thing left is, of course, building a full training pipeline now. Building a pipeline seems scary, but with everything like a small module, it's really not that hard. So here's the game plan. We are going to use a carpool again. We are going to put a step counter and a video recorder so that we can see our trained agent. And this is going to be my transform environment. This is what we are going to make transactions with our agent. For policy, I want to do a DQN, and I want to have a really simple, really small MLP with the Q value module so that I can get the argmax, so that I can do the action that I want, and an equity module so that I can explore and then decay, so that I will see a lot of states. How I'm going to collect this data is I'm going to use the scene collector, and this is going to give me all the next states and all the actions. DQN inherently has a replay buffer on its algorithm, so once we collect this data, we are going to put it into a replay buffer. Once we put it in, we're just going to sample it back so that we have a variety of different samples, and we will use our loss function. Here it's the DQN loss because we are doing DQN this time. We are going to use our loss module to do a backward propagation, step the optimizer, and update my parameters and my evaluate module. And also, since I have 2 modules, which is the target and the policy, I'm also going to do a soft update on the target to deal with the overestimation bias. So this is the game plan. This is what we are going to do. So if you move to tutorial 2, again, we will need to download these things, TensorFlow and TorchRL. These 2 are just for another thing that is optional. So how I am going to build the environment is I will again define my seeds. These are also not yet necessary. So basically what seeds does is it just gives us the option to have a deterministic way of random sampling. So if I have a seed, every random action that is taken will be followed the same. So if you want your training or your module to be replicatable, which means that somebody else can run it and get the same results, you would need to put a seed. So maybe you even heard it from like games. They call it like the seed. The reason that when you put a seed, it just creates the same environment, and everyone knows I'm talking about Minecraft here. It just samples the same thing because every single random step is going to follow exactly the same. So that's why we do the step by the way. I put a step counter into my transform counter, and I also set seed for my environment as well. So in here, in my policy, again, I will do an MLP with Q value module and an eGreedy module. So here's the MLP. I'll do it 64 to 64. I'll wrap it into the TensorBit module. You can just write node, and it actually works. It already saves us a lot of time, but if you don't even want to write the full word, you can also do this. We put the value MLP network. We define the input and output. Now we have a TensorBit module network. And if I put the arguments, it becomes a DPM policy. And if I want to do the exploration that I want, I will put an eGreedy module, I will have an exploration module, and I will just add them together with the torch method. So now, this becomes an exploration policy. DQN also requires a replay buffer, and what this model requires is simply a collector. So what we're going to do is just initialize the collector with the environmental policy that we have, along with the how much frames that I want and how much initial random frames that I want. So initial random frames is basically every action is random, so we have a starting value for our replay buffer. And for the replay buffer, it's going to have 100,000 size for my replay buffer. So everything is done for the optimizing. We are just going to use a DQN loss, and we are also going to soft update our target, and we are just going to use our Google Atom optimizer. The DQN loss is pretty straightforward. We just need to put our policy and the action spec, and everything will be handled through this loss module. And this loss module is going to be connected to my Atom optimizer that I give the parameters to. So here you can also give the learning rate, output 0.02, but it can be anything, probably something similar. And the soft update for the target. And lastly, to see my agent, I'm just going to start a logger, again a CSV logger, and a video recorder. And I'm also going to put the video recorder into my transfer environment. So that, because the video recorder needs to be able to read those pixels. Right? So anything that I haven't showed so far is this training loop. So we can just go through this while this starts running. So what we are going to do is we are just going to use the collector as we have seen already in the sync data collector to get our data, right? And then we will immediately load this data into our replay buffer, so that we can sample through this replay buffer. Then what we are going to do is inside the optimizing step, we are going to sample this data again from the replay buffer. This sample will create us a loss value through this loss. The loss was the loss function. So we are here, the DQN loss. The loss value can be backwards. We also, of course, need to put the loss here. The backward function is going to do the backward propagation here. We are going to step the optimizer, and we are going to zero grad, just so that for the next optimizer step, everything is reset. This exploration module also needs to be stepped so that our epsilon slightly decreases. case, and they just put a step function so that we can easily do the calculation, and we are also going to do the updater step as well, so that our target slowly converges into the Q-value estimates that we have. So the other things are just for the logging that I'm going to pass. So we can see some of the training while I was explaining it already trained. And for the recording, we will begin to render. We're just going to dump. And again, I will just get this torch video and turn it into frame, and we can see what our agent did. So, okay. So, not bad. It's trying at least. It survived for a while. So if we were to train more, we would probably see a much better environment here. But it will probably take a lot of time for us. But even a really small training with nearly under a minute can give us some results. So, so this is everything I would like to cover, and everything that I was going to mention about TorchRL. I hope you guys enjoyed, and I can answer any question. Yeah.
Is there any kind of like broad tutorial explaining all these in kind of animated blog or somewhere or something? There was a whole lot of things that were discussed in it. If we want to go deeper or something like explore these, how this works, or
Yeah, I will share my tutorials into the website so that you guys can replicate what I did. If you would like to learn more, there's a dedicated website for TorchRL tutorial, which most of the material was taken from the TorchRL tutorial website. If you just type TorchRL into Google, you would be able to find. There are also more examples. There are PPO examples as well. It will be a good method to go through, but I will share the slides as well as the code, and then you can do like different variations of formulas. And there are examples of PPO, other modules. Not everything, but another way would be going to TorchRL website, and you can see specific modules and their explanation, what they take as an argument, etc. Actually, I can just do it. So TorchRL, I go in. Here you can see pretty much everything here. Let's say they have a PPO training formula here, and then you can see what they did here, their code, how they define their penalties, explanations on everything. So this could be useful as a and then let's say if you want to search something specific, you can just here LSTM, and let's say I want to see a LSTM module. They have what it takes, the hidden size, number of layers, what it requires. They have like different things, and usually we give those really helps with understanding along with an example as well.
If you don't mind going back to one of the tensor dictionary examples, I was wondering,
In the slides or in the code?
yeah, in the code maybe. Just like connecting the tensor labels to the variables we've been learning in class.
Which specifically?
Like I know you said like the next, and then observation was like S prime. Like what would like done be?
Oh, I see. Like in the beginning, right?
Yeah. Yeah, like one of those.
So here, so what happens is, I have like, so I have the current environment which gives me the observation, right? I reset it. When I reset, I will see the observation. This is like, we call it S. And when I want to step on this, I will use my policy to create an action. This is the A. The moment that I create an action within this given state, I'm going to get the S prime, which is going to be on the written index. So the observation in the next is actually S prime, and I'm going to see the reward, and I'm going to see the done information here. So everything related to here is the one that was the done information, or everything else is in outside of the next is the one before we take the action. So does that make sense?
Yeah, so done's just like a logging of what came before?
Done here?
Yeah.
Done here is either terminated or truncated. So as long as my environment continues to function, I'll get a done of false. And the moment that it's terminated, let's say the poll is falling down, or truncated, if I say don't play more than 100 times that, and if it's on the 101, it's just going to become true. And what is useful for the done is if your environment stopped, and if it's true, you need to go back and reset it.
Right.
So that's why we need the done information, so that we know when to reset.
Sure.
Yeah.
Thank you.
Yeah.
So we're not supposed to use this on our homework, right?
No, so in the homework it's going to be Torch, but I highly recommend using this in your projects, especially if you want to place things around. I think this gives you a lot of functionality. Let's say I want to go for what we should do to make eGreedy really robust, and you can put a lot of things, play it around, don't put it, like remove it, put it back. And since the couple is small, you can just use it really simply. The reason that we don't use this in the homework is because it's too simple. Anyone else? Okay, this sounds good. Thank you for listening.